Welcome to Escape Studio's webinar on Introduction to Houdini. So the next two sessions, we're going to have an introduction to Houdini. So we'll look at the basics of Houdini and understanding sort of how it's different to Maya and other sort of more commonish 3D softwares that other people might be more familiar with, in order to get a better understanding on how it works. I've prepared a couple of slides, basically thinking procedurally for 3D artists. It's mostly aimed at people without a technical or programming background, in order to sort of think differently to get the most out of Houdini. So the big thing you hear about Houdini is it's procedural. So we're going to be thinking procedurally. So out of Maya into the frying pan, or Houdini, you're going to come out of your comfort zone of Maya and have to think in a very, very different way with using Houdini. Procedural software has been around for a while. Side effects, Houdini has been sort of the longest one, over 30 years in production, but there are other procedural softwares on the market, as in Nuke and World Creator and Substance Designer, amongst others. The difference is with traditional 3D software moving to something like Houdini is people always said that the learning curve was very, very steep. It's very, very hard to get into, but once you sort of get over that initial shock, things suddenly become very simple and easy, because once you get it, once you start thinking that way, and that's the idea of these sort of this introductory things, to kind of demystify the differences, so you can kind of understand how you can get the best out of Houdini. That's me, by the way, climbing up the learning curve. So what's the difference between more traditional software or non-procedural software like Maya or Max or Blender versus something like Houdini? Well, you've got to think differently, as I mentioned before. It's a very different headspace. If you come from a programming or coding background, it makes a lot more sense, Houdini, than if you're an artist. Because a lot of the traditional softwares hide a lot of the technicality in order to make it artist-friendly or user-friendly even. So sometimes it muddies the issues, and having all that information thrown at you can sometimes be a bit overwhelming. But as always, one little bit at a time, you eventually build up an understanding. So you're going to think very differently from artist to programmer, as I mentioned before. So you're going to think in a very, very different way, which is quite good, actually, because you can take those skills and reapply them back to Maya and just your general workflow. It will be painful at first, but be patient. It's a painful transition in Houdini. You'll find things take very, very long and it's very confusing, but then one day it will click and suddenly you'll be doing stuff quite quickly and you'll be enjoying it. So let's talk about proceduralism. What exactly is proceduralism? Well, it's a series of well-structured procedures consisting of statements, functions, and commands to complete a computational task. Basically, you can think of it like stepping stones. We process the information in small little chunks. It does one little job, and then it changes the data, and that data gets passed to the next stepping stone, which does its little independent job, which then passes the data to the next stepping stone, and so on and so forth down the list. Now, these stepping stones, and we're not really doing anything inside the scene of Houdini or Nuke or something like that. You'll see nodes, and basically they're little descriptions of what's going to happen. Working this way is kind of non-destructive. These little stones, let me just explain again, actually, these little stones are actual descriptions of what you're going to do. They don't necessarily process the data until you tell it to, until you make an image or you write it out, unlike something like Maya, where you're constantly changing what you're working on in a destructive way, or Photoshop. This isn't it. You're just describing what you're going to do in a series of procedures. That's what those steps are. They're a description of procedures that you will do at some point, but not necessarily at the moment. That'll make a bit more sense once we open up Houdini a bit. The pros and cons are it's non-destructive, the workflow, really, because you're not actually doing anything. In traditional 3D software like Maya, you actually bring the geometry in and all those point information stored within the scene. If you move them, they go to new positions, and that's saved. If you save it, that data is permanently changed. And sometimes if you delete the history, it's difficult to go back. And as you add more geometry, your scene files get bigger and bigger and bigger. Maya, you might think, has nodes, but that history is not procedural. You can't really change the order of them. You can remove some of them, but it's acyclic, the graph. It's actually a DAG graph, a directed acyclic graph, which loops around on itself. It's just a description of, the process of the information. In Houdini, or in procedural software in other hands, the nodes don't store any data. Like I said, they are just a description of what we're going to do. Only when we hit process do they then load the data in, run it all through, and save it out again within that second. But at no point is any real data stored in the scene. You just have a description of what you're going to do. A procedure. The procedures are a description of what you're going to do. We're going to do this, we're going to do that, we're going to do this, etc. Since you're not doing anything, it's not destructive. You can change the instructions if you like, and when you press the button, you'll get a different result. But at no point are you actually destroying it until you output a new result. And the other thing advantage is you can obviously change the order that you do things without any consequence. You'll get a different result, may or may not be what you want, but you can change the order of the process very, very flexibly. It's like building a machine. You know, a good analogy is in something like Maya, you're crafting and sculpting, you take something and you change it over time, and that's your end result. Houdini, you build a machine that will do something. You know, for example, make a vase. So your node is the machine. The different parameters of the vase are the options you might put in for different width or different size or different subdivisions. When you press a button, it saves out to disk a vase, or if you change the parameters, 3 or 4 vases. Whereas in Maya, you'd have to go back and re-finesse another vase again. Yes, you can use Maya's history and get some kind of procedural-like behavior, but it's not strictly the same kind of thing. The machines you can build in Houdini could be much, much, much more complex to, to crazy things like building cities and all sorts of wonderful things. So those kind of machines, if you like, are what the networks can be encapsulated down into what Houdini calls digital assets. And they're like flattened versions of the networks where the most important parameters are available to the artist and everything else is hidden within sort of a hidden network. And these are kind of like the machines of Houdini. They're called HDAs or OTLs, Houdini Digital Assets or Operator Type Libraries. They're either a way to simplify networks, or better still, you can make complete tools and reuse them again and load them back into Houdini to save you having to build that network again. And you can plug them together to create more complex behaviors. They're like your own little mini nodes or programs that you built from other nodes. In fact, most of Houdini is built that way. And the advantage is these days that these digital assets can be run in other digital content DCC softwares, digital content creation softwares, things like Maya, Cinema 4D, Unreal Engine, Unity. So with no extra work, once you've made an asset in Houdini, that'll just run in Maya or in Cinema 4D, etc., which is wonderful because you can make tools not just for within Houdini, but within the other important softwares as well. So inside Houdini, you'll see on the right-hand side is a typical layout of the nodes. These nodes are the procedures. They're mini little computer programs. Each node will take the geometry, the points, look at the attributes, the data on them, do some processing, change some of those attributes. Maybe, one of those is the position of the points, so that might change and deform it. And then it's finished, and it passes its result down to the next node and to the next node. In this case here, we have a box node. This defines vertices, and it's up to us whether those vertices define a polygon or a NURBS, etc. But once that box is formed, it goes to the next node, which then transforms it. Then we play with the normals, and then we make multiple copies, and so on and so forth. So this is a description of what we're going to do. When we actually process for the viewport or we save it to disk, then we actually create the geometry for that frame. But there's no actual data associated with these nodes. These are just a description of what they're going to do to that data. And it flows down these lines, always in the left in Houdini. Now, the nodes are cooked in order. We call them cooking when we process the nodes, and the layout of the network tells us how to cook the nodes. If you look here, Houdini looks for the display flag, and then it traverses left to right, always left to right. So if we look back at this diagram, the display flag is this blue flag here. Is this blue flag here? I'll just wiggle my little mouse there so you can see it. And when we look at that node, we run up the tree, always going left to right. So we've got the left-hand branch up to the very top, and then we'll start at the box. We'll define the box first, transform it, come down to this copy node, which then looks up the second branch. And this second branch looks up the points of the geometry here. So we're taking a point from a grid, then we're copying a box to it. And since there's more than one point, we'll just keep doing that until we've used up all the points in the grid. So we'll get a box on every point in the grid, and then we run further down the network until we finally see the result at the bottom here. So it always processes left to right, and the order of the nodes is the description of the order of the procedures that we're going to run. It's all about these attributes. These attributes are data stored on the points, and the channels are the parameters on the nodes themselves that can ultimately change the attributes. For example, you might have in the transform node, you might scale it up. Ultimately, scale will move the point positions to a different point in space, so it will update the position attribute of the points. These attributes have different sort of classes, as we call them. Point attributes, there's vertex and primitives, and there's different sort of data types, integer, float, vector, etc. Houdini itself, within the network here is basically a file system. So you can access data on nodes by treating it like a file system. The tree view will show you that file system. It looks similar to mine's outliner, but it's not at all. It really is more like Windows Explorer, where each node is a folder, and the data associated with the node can also be accessed as in a path, just like Windows. Within Houdini as well, there's multiple contexts for doing things. There's different nodes in different areas. For example, we have SOPs and DOPs and POPs. This is the language of Houdini. And CHOPs and ROPs and SOPs and COPs. So these stand for operators. So SOPs will be surface operators. You'll spend most of your time in here because you'll be modeling and dealing with polygons and meshes and points. And then normally you'll send that geometry off to another context for processing, for example, DOPs, which is a dynamic operators. So you'll send the geometry information off, it'll do a simulation, come back into SOPs so you can further modify the geometry with textures and normals and whatever else you might want to do. So we often send things off to context and back again. Surface operators is the surfaces, for example, COPs is the compositing. So you might have a texture in the compositing operators, sending it off to the surface operators, which get used when you render the final project. So most of the work is done in SOPs, as I mentioned, because the surface at the end of the day is what you're going to be dealing with. There is one context that appears in them all, and that's VOPs, or VEX. VEX is Houdini's internal language. It's quite interesting, actually. It's the only part, because it's procedural Houdini, you can't thread it or multi-process it because you have to do each procedure sequentially, and you cannot do them out of order, which is a bit of a problem, actually, because you have to do them one at a time. Although that being said, processing the points themselves, instead of looping over all the points, that can be sped up. Now, VEX actually processes all the points in parallel. It does them all at the same time, which often confuses people coming from a coding background, because they assume it's going to loop over the points one at a time, when in fact it processes them all in parallel simultaneously, which makes it very, very quick. So we try and do a lot of stuff in VEX or VOPs to speed up the actual node itself. You know, the node will run very, very fast, even though it's not the actual running of each node one at a time is not threaded, but the actual processing of each node can be sped up by processing the points in parallel using VOPs or VEX. So basically all we do in Houdini, we'll create some nodes to describe a procedure. We may or may not create some attributes to store the data on the geometry, because that's what Houdini does, is worry about the points and store the data. We construct everything else from that. And we might make connections between these nodes which change the order of the procedures that we'll process. Ultimately, that will change some attribute values. We can break connections between these networks and change the way that they behave. And we can also delete some attributes and delete nodes. So that's all we're essentially doing. Mostly, if you're either going to create nodes, break them or connect them together, or you're going to create some attributes and process it and change those values. That's all you're essentially doing, because all Houdini does is see the points and attributes, and it's up to us what we interpret that as. So it's all about the attributes in Houdini, manipulating those, controlling those, and most workflows are that you control those in SOPs, and they'll drive everything else in Houdini. I'll give a little example of this kind of stuff. Other ways to learn Houdini is to look at other people's networks and see the techniques that they use. And you can look at the two forums, the Side Effects forum and the Obforce forum, for some great tips and techniques on how to set up this stuff and how Houdini works. So let's have a little look inside Houdini. And just have a little look at how Houdini can access data and use attributes to control stuff. So I'm just in the technical desktop here with a slight modification, and I like to have the tree view here. In fact, let me bring up the mouse control panel so you can see a little flashy circle. Because on the other machine, it's normally on. There we go. So I have a little flashy circle now so you can see where my cursor is. So up here is the tree view, and this is a file system. If anyone's used the command line or Unix or DOS or that kind of thing, you'll recognize we have a root here, a little /, and then these are effectively folders. If you open up the folders, there's other folders, and this will be a file system, a path. So it'll be /img /comp1 etc. as we go down into the file system. So that's a great way to think of Houdini. Well, that is the way to think of Houdini, as a file system where you can access all this data. I'm just going to create a box for the minute. And I'm going to dive inside. Now, I want to move this box up on the grid, and here I have a center parameter which offsets it. If I put this to 0.5, I can see that it sits on the grid perfectly. That's because the center is half the height. With this set to 0, we can see the pivots at the center of the object. So if I move it by half its height, half its size y, it ends up on the floor. But if I change the size y, I have to change this number to be half that value. Now I can build a relationship between these. And again, this is something typical of Houdini, is to build relationships between things to automate stuff. That way, the user only needs to change the height and it will automatically stay on the floor for them. They don't have to know to change this number unless you let them. So we'll build a behavior. We can also see how Houdini access data. What I want to do is I want to say that this value is equal to this value times by half. Okay? So how do we access this value here? Like I said, Houdini is a path. If I hold my cursor over the word size, we can see it says there's 3 parameters there: size X, size Y, size Z. So this parameter is size Y. This size Y parameter lives in this folder called box 1. And this folder box 1 lives in this object here called box object. If I look over in the tree view, I can see that we have box 1, box object, and that itself actually lives in object, which also lives under root. So the path to this, if I'm going to type it here, would be root, and then we type obj. Now actually we can do it better than this. We're going to use an expression called ch, ch. Ch allows us to read a channel. These numbers on a parameter are channels, whereas these down here on the geometry spreadsheet, these are attributes. As you can see, each point has to have at least one attribute, and that's the position in X, Y, and Z. So ch refers to another channel. So here, I'm telling Houdini with ch, we're going to read the data from a channel, and the channel is going to be this size Y channel. So if I start with a root, Houdini will auto-complete, and like Unix, and you'll see we can see all the folders at the root level. If you look in the tree view, we see the same folders here. I can see that box object 1 is in obj. So if I select obj here and hit enter, so I can either use my up and down arrow keys, or I can click with the cursor. So I'm going to hit enter. We get another // and it's looking inside the obj context and it's showing me all the nodes there. There is only one node at the moment called box object. So if I hit enter again, now it's showing me all the parameters on the box object node and also the nodes inside it. I'm not interested in these parameters. I'm actually interested in box 1. That's this node. So if I select that, now I see all the parameters on box 1. And we can see that size Y is the one that we want. Now I can close my parenthesis and my bracket to finish the string, and now Houdini is able to pull in that data. And you can see we've written ch, read the channel, and then we've given it the path, full path, to this data here. We can see that path kind of at the top of each node. Look, imagine the root there, obj slash box object 1 slash box 1 slash, and then we hold this over here to see size Y. Now, if you want to check the number this is returning, you click on the word, and Houdini will toggle between the value it's returning and the expression. Now, all we need to do is multiply this by half. Now it sits on the grid. So if I change this top number, it's always going to give me a half of that for the center, and now he stays on the floor. And we've built our first bit of behavior in there, and we've seen how Houdini gets the data here because it's basically a file system. Now those that have used the command line before have definitely seen a dot and a single dot and a double dot. A single dot means look here. Okay, so if I put a dot, instead of all this full path, and I put a dot slash, that means look on this folder, box 1, and you'll find this parameter. And you'll see it still works. So we don't have to type the full path. This is called a relative path, or a local path. In fact, Houdini, you don't have to type. Coders never like typing, so we can even get rid of the dot slash, and that'll work. So we call this a relative reference. If we right-click, we can delete the channel, and there's an easy way to make a relative reference. You can select the number you want and copy the parameter. And on the number you want to make the channel expression on, you can right-click and do paste relative reference. You'll notice it gives us the ch expression. If I times this by half, you'll see it works, and it's very easy to do that. So you can right-click copy parameter, and then right-click paste relative reference. Now I'm going to build a similar network to the one we saw in the slide there. So I'm just going to make a curve node. Let's template the box so I can see where it is. In the top view here, oh, there's my box. I'm going to draw a curve. Let's turn that into a NURBS. So on my curve node, this just defines a curve. We've put in a bunch of points. And this can illustrate a point typical of Houdini. We don't really care what these points are. These are just coordinates. It's up to us whether we define that these coordinates become a NURBS or a polygon or a Bezier. It really doesn't matter. All Houdini cares about, if you look here, the attributes, is just the points. It's up to us to define what they are. I'm going to define that as a NURBS because it gives me a nice smooth curvature. If I hit tab and type resample, I can resample this. Let's just say change the options here. I can resample this into 36 segments, which is actually 37 points. This turns it back to a polygon object. If we click on I, we'll see we have a polygon. If we click on the curve object here on the information, we'll see that we have a NURB curve. But the points always stay the same. You know, it depends what we define those points as. What I'm going to do now is hit tab and type copy. And using the copy stamp node, I'm going to copy my box to these points. And you'll see it's copied them lying down. Let me reduce the number of points. And you'll see my little box is lying down. Let me widen the box along the x-axis. Like so. I'm going to look at my box. Now if I look at it front on, if we look at the z-axis, this long edge is the front, this one here. If we look at the copy, they're lying down with the front facing upwards. Now that's because if you look, the z-axis here on our original box faces out this front face. On the copy node, the z-axis now is facing straight up. There's a reason for that. This copy node, as we said before, Houdini uses attributes to drive everything. This copy node is looking for an attribute. See how it's got transformed using template point attributes? It's looking for an attribute called N for the normal. And that's going to tell it which way to orientate the copies. Let's have a look at that. If I hit tab and type attribute create, let's turn on the copy. Oh, let's turn on the attribute create actually and turn on normal display here. This will show the normals. I'm going to set this to N, which is normals. Capital N it needs to be for Houdini. We have a normal attribute here, and you'll see it's one-dimensional. We actually need 3 dimensions because it's a vector. And it needs to be a point attribute here. Now let's give it the value 0, 1, 0, which is pointing straight up in the y-axis. And you'll see nothing has changed. If I change it though to pointing along the z-axis, you'll see all our objects look along the z-axis. If I orientate it along the x-axis, you'll see all our objects orientate along the x-axis. Bearing in mind that the original box here is facing the z, his z orientates himself to the normals. If I turn on the normal display, you'll see the normals here are facing in that direction, and you'll see that the box has orientated itself for its z-axis to those normals. Let's make this 10 so we can see those vectors a little clearer. So as I rotate those normal values, you'll see we can rotate the things around the curve. So this is typical of Houdini. This node here is looking for an attribute on the right-hand side here called N, and whatever that number is, it's going to orientate the copies. We can use that to our advantage. We can calculate N in a different way. Let me disable this node. And there's a great node for doing this. It's called a polyframe node. If we look at the polyframe node, you'll see it creates a normal attribute for us. But it's facing straight up in the Y, which is not what we want. I'm going to turn that off. We have no normal now. It also produces a tangent. The tangent is a vector that's tangential to the curve. So basically it points where the next point is facing. So it follows the curvature. And this is really handy for making forces and all sorts of things. If we change this to n, we're now filling the n attribute with the tangent values. And as you can see, suddenly our dominoes orientate with the curvature of the curve. If you look at the normals, they're all facing towards the next point. So they follow the curve. If we increase the resample, we can see how well that works. And if we re-edit the curve, because this is Houdini, we'll see that the point, they always try and follow the curve. Let's move that just in the X. There we go. So this guy here was just using an attribute called n to orientate our things along that curve. So what happens if you want to use an attribute that this doesn't recognize? Let me just save this quickly. If the saving doesn't in fact crash it. Right, there we go. Cool. So this will always use an attribute called n, no matter what those numbers are. It will just use those numbers for the orientation, which is pretty handy actually. But what happens if you want to start doing more interesting custom things? For example, I might want to have these all at random sizes or a size that's controllable. Let's make an attribute that is size controllable. I'm going to increase the number of points first of all. I'm going to create a wrangle node. A wrangle node allows us to write little snippets of code here to do stuff to our points. For example, we could say at CD equals, we could set this vector to 1, 1, 1, which colors everything white. CD is a color vector. And you see we have an attribute called CD. Technically, we should actually do V at CD, declaring it to be a vector. And this gives us a white color. I want to work out a ratio on the length here. Now we're typing VEX here, and sometimes it's hard to remember the global variables that you can access in VEX. If you make a VOP-net, a point VOP, you go inside, and these are the variables we can access with an at syntax. So things, for example, point number, this is the current point number, or num-pt, which is the total number of points. So in my wrangle, I'm going to make a ratio. I'm going to say f at ratio equals at was it pt num and num pt, that was it. Where are we? Oh. At pt num divided by at num pt. There we go. If we look at our ratio number down here, it's not putting them in. So I think because they're integers, let's see what happens here. So say equals at num pt. We look at that. Oh, let's put the semicolon in. So see the num pt is 40, which is the total number of points. If we do -1, that'll actually give us the point number. There's 39 points. Well, actually 40 points. So if we do at pt num, you'll see that's the current point number. You see ratio here matches the point number. So I'm going to say at num pt divided by, which now gives us a ratio number. We'll do num pt -1 probably. There we go, num pt -1. -1. Now there's a problem here because I'm converting ints to floats. Anyway, yeah, we'll come back to that. I'm waiting too long. I think I've got a question. Can you control scale, rotation, and scale for each box individually? Yeah, that's what we're going to quickly look at. How are you going to learn those variables? Yeah, you don't need to learn those. As I mentioned, if you drop a point VOP in there, they're all listed here. So you just put an at in front of this, so at CD, at N, these are all the variables that you can use if they happen to be there. So yeah, let's quickly look at the scale of the boxes individually. So what I'm going to do is I'm going to create an attribute randomize. And we're going to create an attribute here called height. Let's call it height. And we're going to get a random value between 0 and 1. Let's do between 0.2 and 1, actually. So this is a multiplier. If we look at our copy node, we don't have the attribute come through, but on this node, we do. Let's set the height to 1 dimension. There it is. So you can see we've got a random height value on each point. Now in the copy node, it's called copy stamp because we can stamp that value over. So we've got this attribute called height. What I want to do now is, if you think about it, each point has a different value. This copy node can read that value and affect every time it goes through on each copy and use this number to control something on this side. And we use that through this copy stamp technique. And the way to do that is we go to stamp, we have to turn it on, and then we just type the name of the attribute here. So this was the attribute height. So we'll say we're allowing the height attribute to be used for the stamping technique. I'm going to add a transform node, because on the transform node here, if I play with the scale y, this is what affects the height of the thing. So what I want to do is multiply this with that value per point, and to do that we just type the stamp expression. We refer this using that path, so double dot means come out of this transform folder, and then in the folder you're in, which will be box object 1, you'll see the copy node. You'll see we find it there on the path. And then you, with a comma, notice how when you start to type stamp, it gives you the syntax with an example at the bottom, in case you can't remember. So we give it the name of the attribute here, which was height, and then you give it a default value in case it doesn't work. So I'll give it -1. So if it doesn't work, they'll all scale to -1. That did work, and as you can see, that random value now is being chosen per copy. So this stamp expression is basically saying when we come down this branch, look down here, look up there, look at the equivalent point, read this attribute that you've told, in other words, height, and then bring in that number and just use that number here instead. So since we have a different height value per point, suddenly we get a different height value for each one of these guys. And we can see that if we change the we can't really change the seed actually, but look, we can change the maximum value or the minimum value. You get all sorts of interesting effects. And again, it doesn't matter if we change the number of points or even change the curve. So there's a quick tour of Houdini. We had a look at the idea of how it works, building the data. We look at this node here. We go up the left-hand branch. We start at the box. We come down to the transform. This sees the stamp expression, goes and looks for the attribute on the point, brings in that number, gives us a thing of a certain height, copies it to the position as well. That's what it's reading here, the position of that point. We get one box. And then since there's another point here, we repeat the process until we've gone through all the points on this input geometry. And we get our sort of randomly looking cubes along the curve. So we've looked at accessing data with the channel expression and how we use a relative path to access different parameters. We've looked at a wrangle node, which I've got rid of now very quickly. The wrangle node, as you saw, let's bring that in. We were referring to parameters or making them by doing at, let's call this float at Bob. So I've made an extra attribute here called Bob that's a float. The attribute randomize as well created a new attribute called height. So we've seen how we can create our own attributes with our own numbers in. We even created the normal. We created a custom one here, and then we used the polyframe to mathematically work out the same number, but it was our own custom numbers for n. And by using N and height, we're able to control the direction and also the different scales of these guys. So everything is driven by these attributes on this input geometry here. We've got a height attribute and an N for direction, and then the copy node uses those attributes to make all the copies. And that's the trick to Houdini, is playing with just these attributes and the points and allowing the other nodes to interpret those and create stuff based on those attributes. So I've got a couple of minutes to answer some questions. We've got a question from Omar. To those who are or want to be 3D animators or modelers for VFX, which 3D software do you personally recommend most? Maya or Houdini? Well, that's an interesting question. It depends. I mean, most jobs still will be with Maya, although there's a lot of jobs with Houdini. It really doesn't matter. What's important is that whichever tool you use, you produce amazing looking work. You know, they're not interested in you being clever, they're interested in you in producing amazing looking work. So if it's simple and looks amazing, that's much better than something complicated that doesn't look good. So whichever software you find at the moment that you can produce those great looking images in, that would be the one to use, at least to get yourself a job as a new person. I mean, if you're already a professional using one of the softwares, it's never wrong to learn another. And you know, the more tools you know, sort of the more likely you are to stay and work. There's a lot of Maya-ups out there, but still there's a lot of Houdini jobs too. It's up to you really. Just make sure you produce fantastic looking work in reasonable time, and then that's the tool to choose for you. Everyone's different. Will Houdini work only with scripts? That's from Avinash. You can actually get away without using Vex and stuff, and there's a lot of nodes that do it. For example, this attribute randomize and the attribute create, you can do all of that in a wrangle, but you don't need to. You've got nodes to do that. It depends on the style of work that you want. If you start doing technical stuff and look at those examples online, you'll see people to use bits of code. It's not that scary to script. It's just 1 or 2 lines to do stuff, and before you'll know it, you're building more complicated things. But yeah, a little bit of typing, don't be frightened of it. And an anonymous attendee asked, should we get experience as a generalist first before jumping into Houdini? Also, what sort of math must one learn? Thank you. Again, it depends on the jobs you're going to. A generalist does help because you understand more of the basics of 3D, and Houdini does require you to be technical. An understanding of maths will help no end. Simple vector maths and just how to massage and change numbers is enough to do most things in Houdini. Knowing high-level maths would be a bonus. You could probably do more clever things, but most people don't need to. Just a basic understanding of vectors and being able to take numbers and manipulate them into other ranges that you want, and simple tricks like modulus and little techniques like that. So not too much maths. And again, looking at examples on Oddforce and what people have done, you'll certainly be able to pick up the basic maths that you want to do for that. David Benetti asked, can you explain shortly the relationship between Houdini and rendering? Mantra, Houdini has its own renderer called Mantra. Mantra is awesome. A lot of production facilities use Mantra instead of RenderMan. It really doesn't matter, actually. Mantra itself is very similar to Arnold. It's a physically based renderer, but it's tightly integrated with Houdini, which makes it very powerful and very customizable. So rendering's great in Houdini, to be fair, and it will output to Arnold and any other renderer, really. You know, Houdini was originally a pipeline tool, so it's very easy to get the data in and data out to any sort of system that you want. So yeah, I mean, have a look at Mantra if you're more interested in Houdini rendering. It is a beautiful renderer. Last question. All right, two more questions. So from Thomas Horsley here, do complex scenes take a long time to run and load? It depends. It depends what you're doing. If you're processing lots and lots of geometry, then yes, you know, processing will take. The scenes themselves don't take any time to load because there's no data. You know, you're loading literally just a procedure. What takes time is to then process that graph for the first time to show you the result. The Houdini's nodes are clever. They can kind of cache up. So if you don't make any changes, they cache it. So the next time you process the graph, it'll be quicker. But there are ways, you know, if it's taken a long time to process, we tend to write the geometry out at that point and then read it back in again. So again, depending on how you run your networks, you can optimize them and make them run quick. So generally not. It's not too slow. Thomas Horsley has asked, is a fast CPU important or does it use GPU? As always, with anything 3D, and especially if you're doing simulations, fast CPU and fast GPUs always count. There's a lot of GPU acceleration in the simulation world of Houdini. But so yeah, a meteor of either of those will work, will just improve your workflow. I mean, if you're doing heavy fluid sims, you'll probably want a really good GPU and a fairly good CPU. But if you're doing sort of more animated, other type stuff, then maybe not the GPU so important. But as always with high-end 3D computing, you just need more power is never enough. Enoch Allen asked, are VFX houses still contracting out to freelancers or filling the contracts in-house? That I can't answer. They all do their own individual thing. Okay, last 3 questions, and then we'll end it there. So Anirudh asked, do I need to learn programming languages like C++ to learn VEX? VEX is based on C, so it would help, but no. Like I say, you could probably learn it through learning little lines here and there, reading the docs and sort of reverse engineer it yourself. It's fair, you know, you don't need to write huge reams of code, just do simple lines to do simple things. Harsh has asked, does Houdini have a dedicated animation system like Mash Maya? Houdini is a dedicated animation system like Mash Maya. The stuff I'm doing here you can do in Mash, but I have many more controls over the tangents and the curves and the placements and other stuff. So Houdini itself is Mash, basically. Last but not least, do you need a science engineering degree to become an FXTD? No, I was an FXTD for many, many years, and I did a fine art degree. Not at all. There's a good mix of artistic sensibility and a little bit of technical knowledge. But obviously, the more maths and technical knowledge you have, it'll help. But it's not essential. You know, with this kind of stuff, you'll learn it as you go. You know, it's amazing how much you pick up of techniques of other people, and those little bit of maths will all come together. So no, it does help, but no, you certainly don't. You know, you just need to be fairly bright, fairly inquisitive, and be willing to open your mind to learning and thinking in different ways. So we're going to end it there, guys. Thank you very much for taking the time to listen to me introduce very briefly this half an hour how Houdini kind of works. Hopefully it's demystified a little bit for some of you. So thanks again, guys. Have a good one, and I'll see you next week. Cheers. Bye-bye.